magnetic field. Definitely that concept will help you to understand the operation of three-phase induction motor. Now let me begin with the concept. Now in this diagram you consider this one is the stator core, and on the inner periphery of that stator slots are provided, and in these slots winding will be placed, and this winding will be three-phase winding will be available, and this three-phase winding will be connected in star or in the delta fashion. After connecting in the star and delta fashion, the other three terminals will be connected to the terminal box, and in this terminal box we can provide the three-phase AC supply. When we apply three-phase AC supply to the terminal box, then definitely we are applying the three-phase supply to the three-phase balanced winding in the stator. When we apply three-phase winding, three-phase supply, the rotating magnetic field is going to establish there. Yeah, as you all know that what is rotating magnetic field. Now the magnetic field is that rotating magnetic field as it will get set here. Now I can show with this diagram. Consider that in the stator core there are slots are there. In these slots windings are placed, and in this place only in the winding RMF is induced. This RMF crosses this air gap and cuts the rotor conductors. Here inside rotor will be there. In this rotor slots, in the rotor slots winding will be placed. In this rotor windings are initially stationary. When this rotating magnetic field established in the stator winding, it crosses the air gap and cuts the rotor winding which are yet stationary. As of now, because of Faraday's laws of electromagnetic induction, the magnetic field is rotating. That means flux linking with these rotor conductors are changing. Hence, EMF is going to set in this rotor winding. As EMF gets induced in the rotor winding, rotor conductors are short circuited. Because of that, rotor current induces, and that current starts flowing in the rotor winding. As rotor current starts flowing in the rotor winding, now we can use the definition of motor. The current carrying conductor placed in a magnetic field. That means rotor conductors, now it is carrying a current. It is placed in the magnetic field around this magnetic field is there, that is RMF is there, and in between the rotor conductors is carrying the current. The current carrying conductor placed in a magnetic field which experiences a mechanical force, and rotor starts rotating in the same direction of rotating magnetic field and tries to catch the speed RMF value, but practically it will never catch the speed of rotating magnetic field. This is the operation of a three-phase induction motor. This and I can give one more explanation for this operation by considering the particular this diagrams. Now here in this diagram also what they have shown, this is the stator core, and here this is shown S pole they have shown. If this is the S pole, then definitely here somewhere N pole will be existing, and from N to S magnetic flux is existing from N to S, hence the direction is in the upward direction has shown rotating magnetic field, and its direction is also in the clockwise direction. Now here rotor core is there, and these are the rotor slots. In that rotor slots rotor conductors they have placed. As EMF get induced in the rotor windings, so current also starts circulating. That crossed mark is nothing but current is circulating. When current is circulating in the rotor winding, that rotor winding itself produces the another flux, and that another flux direction is shown in this way. It is in the circular in the nature. This side, this rotor flux and RMF both are in the same direction, hence both the flux will get add each other. But here that same rotor flux is in the downward direction here, but RMF is in the upward direction. So both are opposing each other, hence plugs will get cancel each other. Due to that, what happens, in this side high flux density area will create and this side low flux density area will create. Because of that, force going to come into the picture. That is what's shown in this diagram. Here this side addition of flux will be there, and here cancellation of flux. Because of cancellation of flux, here low flux area will create and this side high flux area will create. Due to that, it exert a pressure or force on the low flux area from high flux to low flux area. Because of that, rotor starts moving, because it is not only with the one rotor conductor, with every rotor conductor same thing happens. Because of that, mechanical force come into the picture, torque produces and rotor starts rotating in the same direction of the rotating magnetic field. And this rotor try to catch the RM map, but it will never catch that speed. Why? That we'll see in the next explanation. So now that this rotor current direction can be determined with the help of Lenz law. What Lenz law states? It opposes the very cause producing it. Now to determine this rotor current, it is saying that it opposes the very cause producing it. So what is the reason behind to inducement of this rotor current? That is the EMF. So why that EMF is generated? Because there is a relative motion between stationary rotor conductor and rotating magnetic field. Due to that, EMF is induced. Hence, to reduce that, reduce the speed of this relative motion, that rotor starts rotating in the same direction of RMF and it try to reduce the relative motion. But it will never catch that RMF speed. If it catch the RMF speed, then what happens? The relative motion becomes zero. It will get vanish. When that relative motion becomes zero, then definitely there will not be any EMF. When there is no EMF, then there is no current. When there is no current, then there is no torque. Then rotor comes to the halt position. But it will not happen in the practical because of inertia of the rotor. But definitely it will never catch the speed of RMF. Hence, rotor speed is always less than the synchronous speed. That is what I have written here with the help of notation. N is always less than ns. N is nothing but rotor speed or actual speed or motor speed, and ns is called RMF speed. So this speed, rotor speed, is always less than ns, that means synchronous speed. Hence the name of this induction motor is also called by asynchronous motor. While explaining yesterday's video, that means in the part 1, I called induction motor as a asynchronous motor, and I told I will tell you why this will call it as a asynchronous motor, because of this one, because of this reason only. Why? The rotor speed is always less than the synchronous speed. With the help of this explanation, I am going to conclude today's lecture. I hope that you have understood how exactly induction motor start operating or start rotating. This is the reason behind it. Thank you.